finish up my class and lecture on ocean renewable energy. And then we can have a short demonstration experiment led by Jihu, TA. And then we can go on to the next topic on underwater acoustics. Probably because next Tuesday is available, so we can push the second part be delayed. And also the first part of Smart Shipyard can be shown on next Tuesday, also including the bracket discussion session. Right. Question on schedule or any other things? And I can go on to we stopped around here. Right. So the aquatic biomass energy to reduce the land utilization. We can use the ocean surface for the energy cultivation. So natural basin water area or artificial water area. Or it can be ocean, it can be river. So coastal area can be good. Area can be used for such a cultivation, farming. And also fishing farm can be coupled with this aquatic biomass growing field, because the fish can eat some of the byproduct of the biomass. So there are many research topics we can do, because it can help the water treatment. That means we can improve the environmental issues, pollutions. Let's see the video.
What is aquatic biomass? Aquatic biomass is made up of microalgae, seaweeds, and marine plants. By photosynthesis, it produces half of the oxygen we breathe. We can use aquatic biomass as a base for many useful things, such as chemicals, inexpensive biofuels, and food, including more valuable omega-3 oils. Aquatic biomass is great news for a bio-based society. Why? Creating products from aquatic biomass does not require a lot of fresh water or agricultural land, and the produce is CO2 neutral. Take fuels, for example. The CO2 released upon combustion is withdrawn from the atmosphere by the existing aquatic biomass. This drives the photosynthesis process. If we want to produce aquatic biomass in our oceans on a large scale, we still have to solve a lot of biological, technical, and infrastructural problems. At Delft University of Technology, we take this challenge by working on cultivation processes that are robust and simple. If you want to find out more about ocean energy,
right. And there is another video on algae farming.
We all need fuel to get around, and as America takes steps to improve our energy security, homegrown fuel sources are more important than ever. The Energy Department is researching one of the fuel sources of the future found here in algae. Have a look at this algae farm. These large man-made ponds are called raceways, and they cultivate a new crop of algae every few weeks. You see, algae, or more correctly, microalgae, are very small aquatic organisms that convert sunlight into energy. Some of these algae store energy in the form of natural oils. Under the right conditions, algae can make a lot of oil that can be converted into biofuels. Algae could potentially produce up to 60 times more oil per acre than land-based plants. Extract that oil, and you have the raw materials to make fuel for cars, trucks, trains, and planes. In the future, anything that runs on gasoline and diesel could also use biofuel from algae. The oil is extracted by breaking down the cell structure of the algae. This can be done by using solvents or sound waves. After the oil is extracted, then it is further processed at an integrated biorefinery, or in the future, at a traditional oil refinery. Another great benefit of algae? Consider this. Like plants, algae needs carbon dioxide to grow, and that's good for the environment since it takes CO2 out of the atmosphere, making it a nearly carbon-neutral fuel source. There may even be opportunities to build algae farms next to power plants that use fossil fuels, actually using CO2 exhaust to feed algae ponds. There are over 100,000 different strains of algae. Some grow better in different climates, or in freshwater, saltwater, or even wastewater. So, scientists are testing different algae under many different conditions to find the best strains and develop the most efficient farming practices. While commercial production is still a ways off, algae holds great promise to become a reliable homegrown fuel source to reduce our nation's reliance on foreign oil.
Okay, so it is about algae, and source of biofuels. Comparison: corn, soybean, canola, jatropha, coconut, oil palm, and microalgae, and hectare per liter. So yield is much higher than land-based bio crops. So in reverse way, required land area per some standard size, and that is reversely smaller, right? And percentage is very small now. So most of the corn and soybean is the most popular in United States. So this is algae farm in land side, but also they use water area near, or is it inside land side, right? But now it is a Korean project on ocean aquatic biomass energy for production, including, right? So there is a big scale area as a pilot plant, and then they also develop devices to planting algae or biomass, and then collecting them, and then transport to the processing unit. All right, that's it. A short summary of this. And we finish up renewable energy process. Right, so we can then continue our small experimental demonstration by TA, please.
Okay, so can everybody hear my voice?
Yes.
Okay, so this is my experimental lab, and this big water tank behind me is filled with water, and I have prepared a
How can I enlarge the screen the experiment shows? Because your sound is coming from different source, right?
네. 지금 그 이 웹캠 화면에 오디오가 연결되지 않아서. 들리시나요?
네, 들리긴 해요. 근데 저 더블 사운드 들리네.
잠시만요. 지금 혹시
예,
괜찮나요?
빅 스크린으로 나온다. 예.
네. So it's a bottle filled with water with some amount of air inside, just like you can buy from any other stores. 그냥 바로 넣으면 될까요?
네.
So I'm just going to put this into this water tank. And you can see it's floating on the surface. 잘 보이시나요?
예. It's good to see. It looks like an iceberg, right? Very small portion of the bottle is above the water, almost submerged. So you can see that the specific weight is almost similar, same as the water. We already solved this problem as a midterm, 그죠? Jiwoo, do you have another specimen that can be going down to the bottom? Or you can open the cap and then close the empty portion into full of water, then try again.
Put this up and let it just fully sink into the water.
And then you need to close the cap again. Right. So what is your expectation, student? We don't know, right? Because the density of the plastic. It's going down. All right. So there is a very small difference of buoyancy and weight. Very small difference. So you may see that usually the Navy submarine is in this situation. A little bit higher weight than buoyancy, but almost neutral, but a little bit higher, so that it can be flying or navigation using the dynamic lifting force. But once, as Indonesian Navy submarine, once the engine is stopped, then there is a high potential of this kind of situation that slowly the submarine is going down into the deep ocean. What is the question? Why does the bottle turn over when it floats? Why does the bottle not float with the cap on the top, even though it has air? But because air is moving around, so they find the better position. Air is free inside the bottle, so they are moving, and they found the best position, I guess. I don't know. We need to have a more detailed calculation to find out, or if we want to predict which one is the correct position or optimal position for the air escape. But anyway, the air, of find out the best position for them inside the butt. Right, that is my answer. Do you have any other better question? Better answer? Balance the moment created by the buoyancy. Yeah, you're right. They are trying to balance. Yeah. So if we somehow make very gently putting them, maybe the cap side can be stay in that position. But it is an unstable situation. So they try to find out stable position. At the top of the bottle, it is unstable. All right, so that was a short experimental demonstration. Actually, I tried to do this one in earlier stage of class before the midterm exam, but it was much delayed. But anyway, thank you for Jihu for making demonstration today. All right, what time is it now? 7:50. So we can continue our present class. So I will continue my slide sets. All right, this one. This one is about underwater acoustics. So this is about chapter 8 of second textbook. And this chapter is divided into two parts. And this presentation is about sound itself and acoustics and sonar and sonorization. So this chart shows the sound level, but level is going up into the down of the figure. Going down, it is bigger sound. So at the bottom, you see that airplane, gunshot, and trucks are running, helicopters are running. Right? In the top, there is a small sound such as water dripping, and what is this? Watch clock is clocking, and bird sounding, and also very small sound is plant, wood is growing sound. So sound and acoustics. Sound is a mechanical wave, right? Pressure wave, we can say, but a kind of wave. Okay. We already study about what is ocean surface wave, but this one is not visible, but there is a sound wave coming towards our ear. And that oscillation of pressure transmitted through medium. Medium can be air or solid or liquid. So inside the water submarine, they use water as the sound transmission medium, which is detected by the receiver as a change in pressure. So our ear is working to sensing the pressure changes inside the air. And acoustics is defined as a science that deals with the sound, right? And production, control, transmission, reception, and effect. So same once again. The decibel and or micropascal. But anyway, sound pressure level with airplane and also very small sound can be tree growing or inside the bedroom. Now we go on to underwater acoustics. Leonardo da Vinci in how many years old? 500 years ago. If you cause your ship to stop and place the head of the long tube in the water and place the ear, you hear ships at great distance from you. So if you dip your ear inside the water, you can hear other sounds well. You may try yourself inside a water bath when you do a hot tub bathing after shower, not shower, but inside the hot water. You can dip into the water, including your ear inside the water. Then you can hear many other sounds more clearly. So that is the idea catched by Leonardo da Vinci. And inside the water, the transmission of sound is better than in the air, and faster and larger. So that's the reason we can use sonar as the communication device inside the water. So application area, sonar, underwater communication, localization, navigation, and seismic exploration. That is all related with the sonars. Right, here is the sound mapping, or there is a survey ship using sonar. So there is a source of shock wave or air gun is transmitting big sound toward the water. And you see that there is a hydrophones, an array of hydrophones. Hydrophone means receivers. And then the top layer is a seabed. So it's a soil. The water is very pictured as a shallow, but it can be a deep water. But anyway, and below the seabed, the ocean bottom surface, there can be layers of different rocks and other soils, right? And at the bottom, you see that there is an oil reservoir, or oil and gas can be detected using that kind of survey, right? So first, when oil field is explorated, first thing is you should see the map of the area, and then you can find by seeing the situation in the area that there can be a higher possibility of area. Then you put this kind of survey ship to get the sound mapping of deep into the earth below the seabed. And then reflected sound wave is catched by hydrophones. And by using this one, it is very similar to radar, but using sound radar. Right? So very weak maps can be created. So how does sonar works? Sonar use sound echoes to locate object, as does radar. Right? Very similar to radar. So sound is generated somehow, and then its original wave is going, and then the object is reflect wave, very small reflected wave is going back, and then the speaker and then receiver is same here, sender and receiver, so that it catch the return sound and then catch the, probably expect where is the object. And that is very same as the animal who is doing bat or dolphin. So human body is copy the idea of animals this way. So why sonar? Why not using radar directly inside the water? Because the electromagnetic propagation, which is based on radar is based on electromagnetic waves, but is not coming through the water. Big losses, so it cannot go far away. It is only short distance is disappear. All right. Oh, something is large distance. Okay. And this is absorption spectrum or attenuation coefficient based on versus wavelengths of liquid inside the liquid water, and also atmospheric water vapor and ice. So as what is this? The horizontal axis is wavelengths. So higher frequency, and you can have a more loss of energy. That's why sound can be sound and light is all wave. Both are wave, but the wavelengths is very different. Right? Wavelength is very short for the light. Then that's why the observation or attenuation is very high. That's why we cannot use sound. We need to use sound inside the water. Or electromagnetic cannot be used, so that we cannot use radar inside as a submarine. So underwater communication can be three types. One can be electromagnetic wave, that is light, or wave, same as radar, or smartphone, or radio, and optical, there is a light wave, and acoustic wave. So there are three possibilities, but practical use can only be done by acoustic waves. The others are very short. And this is the way we are using sonar system to detect enemy submarine. So same as before, that there is a sound source and there is a hydrophone array. Because the array is long, because we want to detect more wider area. Let's see a video again here. Oh, this is not video. This is paper. Okay. Okay, the image is coming from the paper. Okay. And first idea was electromagnetic wave, but I told you that it is not working. But why? We see that using electromagnetic wave, the communication can be established at higher frequency and bandwidths. But the limitation is due to high absorption or attenuation in water. So that we practically we can use big antenna, maybe help, but that is very complex and cost-wise is not economical. so it's not used well. Optical wave is similar too. Also offers high data rate transmission. It is same as electromagnetic wave. The bandwidth is very good, so more information can be transferred if we can use electromagnetic wave. Same as the smartphone, we use electromagnetic wave, right? So bandwidth is good. So that's why we are using electromagnetic waves. So optical wave is similar, right? Data rate transmission is good, but it is also have a problem of absorption and also scattering. That's why we are not using, only using sound. And speed of sound in different material. Air, we already know that it is 340 or 30 meter per second. But inside the water, the speed is about 4 times higher than air. The speed is very fast, right? 4 times higher. And inside the metal, that is also much higher, right? Okay. So acoustic wave is the almost the only option inside water. So most preferred signal used as a carrier because of its low absorption characteristics. But the problem is data transmission is slow. Speed is slow and the bandwidth is small. So that the data transmission rate is very low. Bit per second is very low. But the range, the distance it can travel is higher. So there is a active and passive sonar. So active sonar employs the sound generation. Sound is generated by something, and the receiver to record the returning echoes. So we see this kind of system in previous slide. So sound is generated, and then we also sensing the returning back reflected sound waves. But passive sonar only listens, it does not send any sound from them. No generation of sound, only receiving by other ships and submarines. This is important when there is an enemy vessel. You cannot generate sound because then you will be catched by the enemy, right? So each one trying to be very quiet. So you may remember the submarine film from the World War II between Germany and US or other country, England, UK. The submarine battle, they are very trying to be quiet, both sides. Only listening the enemy's sound coming. So here is the sonar equation. The sonar equation means for determining the effect of the medium, target, and sonar equipment on sound propagation. So we are using decibels. We already see what is decibel. Compares the power or the intensity of sound at one point in standard logarithmic scale. Right? So we call say power gain, log 10, P in, P out. So it can be an intensity level or scaled sound pressure. So pressure is the we are trying to catch or sensing. And sound propagation. Sound is a wave, right? So it's a spreading out. It depending on the source of the sound, there can be a spherical spreading or it can be a cylindrical spreading, and and there can be a loss because of the spreading out. The sound level can be lowered down because of the distance. Right? So we need to calculate absorption coefficient because absorbed by the water, and also there is a transmission loss due to scattering. This is the biggest one, A. So you'll see that there is a spherical spreading. This is the same as light. So you see that this is light bulb. But sound is the same. The intensity coming from the point source, but goes out to all around the sphere. You can calculate S. S is in this equation, A. How much is scattering out. But if you have a line source, something like a light bulb in our house, there is a long, lean and long light bulbs, right? About 1 meter length. Then the spreading can be cylindrical. So it can be better than the point source. And the sound source and noise from the ship or submarine, you see that there is a machinery noise coming and flow noise and fouling also create sound at the skin of the surface of the ship. And there is also cavitation. Cavitation comes from the propeller, right? Propeller, because of the rotation on inside the uneven pressure field. The water pressure is lower in some region, higher in another region. So it's a fluctuating water pressure level there. So when the water pressure is low, then air is bubbling or boiling of the water and collapsing again. There's cavitation. We already see this. And ambient noise is also there. That is coming from the outside. Biological noise, something. All right. Oh, this one is very small pictures. And anyway, there is at the bottom, there is a frequency levels. And the vertical, there is a sound levels. And what is this? Sound levels of the other items. And at the bottom, they are saying seismic background and turbulent pressure fluctuation, ocean traffic, and bubbles and spray, and molecular agitation, and surface wave. So frequency is low in surface waves and seismic background, something like that. But at the top layer, there is a big sound, right? So earthquake and explosion is very low frequency, but it is a very high decibel level, big sound. And biological and precipitation, ship and industrial activity and sea ice can also be a big sound. And in the middle, there is a numbers. They are saying sea state. Sea state is a wind levels or sound wave levels. When the storm is coming, we say the sea state is very high. And 6 level, it can create a much big sound. The frequency may be a little bit different, but anyway, this shows a curve of blue colored curves. And precipitation is coming from raining, right? Rain or mist or snow. We call this as precipitation. It is here, precipitation in the top layer, third ones. And then active and sonar and passive sonar. Active sonar is they are sending or generating sound, right? And passive sonar does not have generate a sound. So there can be a echo level and noise level is come together. So the source level is SL and target strength is TS, because target can be enemy submarine at the bottom, black enemy submarine. So noise sound is generated by sound level SL. So we can calculate, and by using this equation, you can expect the distance and directions and something like that. So in here, you see that all the parameters inside the equation: source level, noise level, directivity index, and detection threshold, and transmission loss, and target strength. Oh, here is the video. So let's see. Okay.
You're diving in the ocean when suddenly a large military submarine sails next to you. Question: how can this vehicle harm you? Well, the possibilities are endless, but the one way you probably didn't think of was sonar. Sonar is an acronym that stands for Sound Navigation and Ranging, and as the name suggests, is used for navigating and ranging objects underwater. Sonar is used because sound waves travel through water much better than radar or light. Since submarines, especially military variants, typically do not have windows, sonar is a submerged submarine's eyes. There are two types of sonar, active and passive. Passive sonar simply listens to the sound of the water. It listens for marine life and other ships that may be nearby or using active sonar. Active sonar, on the other hand, actively sends out pulses of sound and listens for how long they take to return when they bounce off an object. Sonar works by calculating the echoes. Once you know the speed of sound in water and the time it takes for the signal to return, you can determine an object's distance. And this is a type of sonar that could potentially harm you if you were diving next to a submarine for some reason. So how can it harm you? Well, sonar is a sound, a very loud sound. A sonar ping can be as loud as 235 decibels. To put that into perspective, the loudest sound you can hear before your eardrums rip apart is about 160 decibels. Above 194 decibels, sound waves become classified as shock waves in the air. In water, however, sound can get much louder. Getting hit by a 235 decibel sound ping will likely burst your lungs and cause your brain to hemorrhage, which in most cases will kill you. But if you're lucky enough to survive, you're probably not going to be in great condition. What about bats? Bats also use sonar and they don't burst lungs or hemorrhage brains. Well, the reason for that is simple. Bats are not submarines. More specifically, bat sound frequencies are in the ultrasonic, ranging from 20 to 200 kHz. Human hearing tops out at 20 kHz. These sounds can reach up to 120 decibels, but since they're ultrasonic, we can't hear them. Scare tactics aside, it's unlikely that a submarine will use its sonar to casually distress a swimmer, as a sonar ping works both ways. It helps you find things, but it also helps things find you. A submarine's biggest advantage is its stealth, and using what is equivalent to a massive beacon is a bit counterproductive to this goal. On top of that, ships aren't really allowed to use sonar within 12 nautical miles of the coastline to avoid damage to marine life, which includes swimmers. If these ships detect marine life of any kind, they have to turn their active sonar down or completely off. So perhaps submarines are not your biggest threat in the ocean.
All right. So we see that's how the sonar works. Oh, that's already finished. So that is it. It is too early to finish. Then we may see some of the slide for the second part. Any question? Yeah, all the students. There. Oh, Brock is here. Return, Brock. But did you see the new schedule that you will have the discussion on next Tuesday? Market. You are not listening to me. Any question? No. Then we may start a little bit about the videos. No, the second part of the presentations. This one. Okay. So we'll see more on speed of sound and sound propagation in the ocean, and then application systems. Speed of sound. There is a Newton-Laplace equation. I hope you already see. And there is a bulk modulus in the equation. So you see that we already see from previous slides that speed of sound is increased with the stiffness of the medium or elasticity, and decrease with the density. Right? So in the air and in the water, the speed is different, right? You already see this, the difference. In water, the speed of sound depends on the temperature, pressure, and salinity. In addition to the density and other things, density and bulk modulus or elasticity. So it is small difference, but between waters, among waters, you should know about difference in temperature and pressure and salinity, so that what sound runs different speed, a little bit different, but due to this small difference, the sound or sonar can have a big changes. Right? So it increases with temperature, salinity, and depth, the pressure. So empirical formula by a person is something like this. Here is the sound of speed, temperature, salinity, and depth or pressure. So that because of these differences, usually the temperature of the water is going cooler in the deep ocean, right? So temperature in surface, near surface is higher, usually because of sunshine. But it is not going smoothly. It has zone differences. So the gradient, the slope is different between zones. And that gives you differences in sound travel or speed. That's why, because of the speed of sound has a different profile like this one. So this one gives you very big difference in sound traveling. Anyway, we call this is 3 zones. As first zone as a surface layer. It is thermocline. And second layer is a main thermocline. And third zone is a deep isothermal layer. So usually the temperature is down, but pressure is up. But in this, say, here is a temperature and depth pressure is going together, right? Temperature up, speed up, pressure up, speed up. But the real situation is temperature is down and pressure is up. That's why it is very complicated situation like this, speed differences in water. So in deeper water, you may see that sound speed is increasing. wave refraction. Refraction is when sound is change their direction. Okay? So there is a Snell's law that what can be the angle depending on the velocity of the wave and because of the density of the mediums. And you see, remember that reflection, refraction, and diffraction. So we are talking about refraction. Refraction, the angle changes. Diffraction is scattering and different ways. And because of these regions, sound velocity regions, and slope is different, there can be a deep sound channels. And there is also called the shadow zone. Because of this sound travel differences of speed. When you have a sonar here at the star, red star, the sound is reflecting from the sea surface, and also travel speed is different. And there is a shadow region, so it can be very dangerous to this. The sound tends to be focused between negative gradient of the main thermocline and positive gradient of deep layer. Anyway, within this channel, low frequency wave may travel thousands of kilometers, very long distance, right? So this can be thousands of kilometers, long distance. So it's good. But anyway, there's shadow regions. One more slide, then we can start. All right. Okay. Oh, application systems. There can be many application systems. Active echo ranging sonar. We already see from previous slides that we use sonar to detect oil reservoir underneath of the sea bottom. Also, submarine use detecting enemy and other things. And multi-beam echo sounder. There's several sound is going together. And side scan sonar. So they have a long range of sonar arms to detect more wider area range. And sub-bottom profiler. So the bottom of the seabed can be mapping or profiled, check their shape of the sea bottom. And sonar buoy, and dipping sonar. Dipping sonar is some sonar devices dip into the water. Sometimes the helicopter has a dipping sonar, so they stay above the water surface as the helicopter is flying and staying there, and then they lower down the dipping sonar into the water to check the sound of the enemy submarine something. And communication is also important, so we can use sonar as a communication. And positioning and navigation systems for submarine. They need to know where is my position there, okay? And surveillance system. All right, so that's enough for today because it's the evening class. We may stop a little bit earlier. Question? No questions. So I hope Bearcat generate more discussion next time on Tuesday. All right. Thank you, Jihu, for the experiment again. And see you next time on Tuesday. Bye now.